Hi guys, this is Dr. Tim Kruse, Elementary Statistics. In this lesson, I'm going to demonstrate how to find confidence intervals for the difference between two means, two population averages. Mean means average. All right, we're going to use a formula that in general form looks like this. Now the margin of error, that's kind of the give a little bit, take a little bit. So I'm going to say, well, the difference of these two population averages is between, and I'm going to say, well, I'm going to guess at it with my sample averages. I think it's this, give or take a little bit of error, give or take a little bit of standard deviation. Now, standard deviation, this error, this margin of error can be calculated two different ways. I calculate it using the z if I know the population standard deviations. So if I know both of the sigmas, I'm going to use a z-score to help calculate my margin of error. And if I don't know both of these population standard deviations, I'm going to use a t-value. All right, so I'm calculating margin of error both ways, and everything looks really similar. If I know sigma, if I know population standard deviation, I use a z-score. And if I don't, I use my sample standard deviation, S for sample standard deviation, and a t-score. All right, but those are the formulas we're going to be using. Also, when you're using the t-score, when you don't know sigma, you just know your sample standard deviation, and you have two different groups, we're going to need to calculate degrees of freedom to look this number up in the table. And if your groups are different sizes, we just use the lower group, whatever the smaller group is, we'll use that for degrees of freedom. I'll show you that in a minute. Just make a note of it for right now. All right, so what we're discussing is we're just kind of asking ourselves, are two population means, two population averages, are they different? Not only different, but are they significantly different? Like, are they different enough that it's a big deal? You know, does anybody care? For example, if you think in a classroom and you look at the tallest person, you know, maybe they might be 7 foot tall, and the shortest person might be 5 foot tall. Well, that's a big difference. That's 2 feet difference. That's significantly different. But if I stand two people up next to each other and one of them's 5'6" and one of them's 5'7", well, that's not really different enough to matter. Everybody's going to say, yeah, they're about the same height. It's not going to be the same thing as the tallest versus the shortest. You stand them side by side, and it's going to be obvious that this one is really tall and this one's really short. But if you stand these two side by side, it's not going to be real obvious. The difference is not enough to matter. So significant is the word we're looking for here. Are they significantly different? All right, what I've drawn here is a 95% confidence interval. So that's from negative 1.96 to positive 1.96 if I'm using the z-score. That's between the 196's is 95% of the area. So that leaves 2.5% over here on the left tail and 2.5% on the right tail for a total of 100% if I'm using the z-score. Now I put an example under here. If we're speaking z, we're talking about the 0, 1, 2, 3 numbers. If we're speaking x, we're talking about numbers that came from our word problem, our story problem. And I just used an example of average ACT scores. So when high school seniors and juniors take the ACT, the average score is 20 on the ACT, and the give or take is about 5 points. So give 5 points takes you up to 25, take away 5 points gets you 15. So the average, or the population mean, is 20, and the standard deviation is 5, give or take 5. Now looking at this, I'm just going to throw a couple values up here. Is 20 versus 30, if one class has an average of 20 on the ACT and another class has an average of 30 on the ACT, is that significantly lower? 20 is obviously lower than 30, but is it significantly lower? And we'll look at a couple of examples like that. All right, so using that curve up above, let's say, for example, I take a sample of one classroom, and the average of my sample, X bar stands for average of my sample. If I average the ACT scores in that classroom and their average is 20, and then I go to a different classroom, maybe it's in another school or another state, and I find their class average. So I sample the ACT average for that second classroom, X bar 2, the second classroom, and maybe their average is 30. Maybe they did a lot better. Okay, it appears that group 1's average, sample average, is lower than group 2's sample average. Okay, it's obvious that 20 is lower than 30, but is it significantly lower? Now, when we run it through the equation, through the formula, and I'll show you how to do that in a minute, I just kind of jumped to the end here and I said, okay, the difference between the two population averages is between negative 12.53 and negative 7.47. All right. Well, the point I'm trying to make here is if both of these numbers wind up being negative after you run them through the formula, if they're both negative, then we can say, yes, group 1 is significantly lower than group 2. You can't just look at it and know, all right? You have to run it through the formula before you can make a decision. So if both of the numbers wind up negative, you can say, yeah, definitely, group 1 is significantly lower than group 2. Excuse me. Well, what if I switch it? What if I say group 1, maybe that's an Oklahoma classroom, and their average ACT score was 30 out of the people that I sampled. And then I go to another classroom, maybe it's a different part of Oklahoma, or maybe it's Kansas or Arkansas or whatever, and their class average is 20, all right? It appears that group 1's class average is higher than group 2's class average. 30 is obviously higher than 20, but is it significantly higher? Well, I'm going to run it through the formulas. I'll show you here in a minute, and I'll say, okay, the difference between the two population means is between, and I came up with these two numbers here, which are both positive. If they're both positive, I can say, yes, group 1 is definitely significantly more than group 2. If they're both positive, group 1's average is significantly greater than group 2's average. And then finally, what if group 1's average was 20 and group 2's average was 21? Well, that's not very different, all right? I got to calculate it and see if it's significantly different. It appears that group 1's average is 1 point lower than group 2's average. So group 1's average is lower, but is it significantly lower? Does anybody care? Is it low enough to make a big difference? Well, if you do the calculations and you wind up with a negative number and a positive number, so I'm saying the difference between the two averages is between this negative number and this positive number. If you have both positive and negative numbers in there, there's no significant difference between the two groups' averages. So I can draw no conclusion between these two. It appears that group 1's average is lower, but I can't really say that with 95% confidence. All right, I can't say I am 90% confident that group 1's average will always be lower than group 2's average. I can't say that because they're so close together that it could easily go the other way the next time I take a sample. All right, so let's try a problem here. Is the time between Old Faithful geyser eruptions getting longer? All right, that's called an interval. All right, they're measuring how long between eruptions. And they measured it over two different time periods. They said from 1948 to 1952, we observed it 8,980 times, and the average time between eruptions was 61.8 minutes. Now, in another time period, from 83 to 87, they observed it a whole bunch of times, 23,936 times they observed it, and the average time between those eruptions was 69.8 minutes. All right, so X bar 1 is 61.8. This is group 1, the early time period. That's X bar 1, our sample average for group 1. This is our sample average for group 2. This is X bar 2. Now just visually it looks like group 1 is lower than group 2, but we have to run it through the formula and see if it's significantly lower. You know, those might be close enough together that nobody's going to worry about it. If they're significantly different, then the scientists, they start to worry and they start to wonder if something's going on because the time periods are so significantly different. So let's work this out and see if they are significantly different. Historical data suggests, that just means it is known that sigma 1, that's the population standard deviation for group 1, the older time period, was 8.56 minutes in between eruptions. And for group 2, that's the more recent time period, 83 to 87, the standard deviation for group 2 is known to be 11.57 minutes. These are population standard deviations. If you know these, that tells you to use the z-score in your calculations. So I'm going to organize my information. This is group 1, this is group 2. So how many, n, number, how many were in group 1? We had 8,980 observations. Here's my population data, my population average, population mean, same thing, and population standard deviation. We don't know what the true population average is. It's unknown. They didn't give it to us. We're going to guess at it using the formula, using our sample. So our population average is unknown. Our population standard deviation they gave to us as 8.56 minutes. So give or take 8.56 minutes. We made a sample. We observed 8,980 eruptions. That's our sample, and on average it was 61.8 minutes in between eruptions. That's our sample. Our sample standard deviation is also unknown, but it's not actually necessary if we're using the z-score in our calculations. So it's unknown, but I don't care. We don't need it. We're going to guess at mu using x bar. We're going to guess at the population average using our sample average. Same thing for group 2 over here. All right, the more recent time period. In group 2, we observed 23,936 observations. The population average interval between eruptions is still unknown. That's what we're trying to guess at with the formula. Population standard deviation for group 2, they told us was 11.57 minutes. And our sample, based on these 23,936 observations, our sample average was 69.8 minutes in between eruptions. And then our sample standard deviation, again, is unknown, but we don't need it if we're using the z-score in our calculations. They told us find a 95% confidence interval for the difference between the two population means. Confidence level 95%. We're using the z-score, so I need to look up the z-score that relates to that confidence level, which means the z-score as it pertains to 95%. And we looked that up in the z-table at 1.96. Now, more accurate is better, all right? 1.96 is probably fine, but if you guys ever find that you can't get exactly the answer that you're looking for, it just means that you need to make your z or your t-score more exact. Now, most of the time, 1.96 works just fine, but if you're off just a little bit and you can't get the answer you're looking for, try using a more exact z-score. So here's the more exact z-score. All right, now let me review how to get that 1.96 z-score. If you have a 95% confidence interval, that means you want to fence in 90% of this area. All right, think of this as a fence or a boundary. You want to fence in 95% of this area, and you need to know what z-scores form those boundaries between what two numbers. Now, I told you it was 1.96. Let's review how to look that up. Think about your curve. If there's 95% here, right smack dab in the middle, that means there's 5% left over for the tails. If I take that 5% and split it in half, that means there's 2.5% here and 2.5% here. I'm going to concentrate on this 2.5% over here because I can look up area to the left in the z-table. So if I think this is 2.5%, if I calculate that this is 2.5%, that's 0.025. I'm looking for a negative z number that has an area to the left of 0.025. So I grab my z-table here and I look for an area of 0.025. There it is right there. And I see what z number produced it. The z number of negative 1.9 and then go up to 6. The z number of negative 1.96 produced 0.025 or a 2.5% area. So that's where I got this negative 1.96. And then since this is smack dab in the middle, that means its positive twin over here will be the other fence or the other boundary. So look up 2.5% in your z-table. That gives you this negative number right here. And then the other one will just be its like positive twin, and that will bracket 95% of the curve. Now, if you have a nice confidence interval table, mine came with this nice confidence interval table here. It's nice because they already have it all figured out for you. A 95% confidence interval means everything in between both of the 1.96s. And if you want a 99% confidence interval, that's everything in between the 2.58s, from negative 2.58 to positive 2.58. Sometimes they say 80%, that's everything in between the 1.28s. All right, if you have that table, you might want to copy this down. It's handy to have. If you don't have that table, it's pretty easy to calculate. All right, and then finally, I want to show you how I got the really exact Z number on my calculator. So remember, this is 2.5% to the left. So I'm looking up what Z number produced 0.025. And your 84 will do that. It's under here, under distribution, this right here. So second function, distribution. And what you're looking for is called an inverse norm, inverse normal curve. We're talking about a normal distribution, but you're doing it backwards. Inverse means backwards. So instead of giving them the Z number and them telling you the area, we're going to do it backwards. I'm going to give them the area, and they're going to tell you the Z number. So I'm going to do a backwards normal curve. I'm going to give them the area. Let's hit enter. And they say, okay, what area do you want? Now I want 2.5% over here. So 2.5%, you got to enter it as a decimal, 0.0250. They said, what's the average and what's your give or take? What's mu and what's sigma? Your population mean and your standard deviation. Well, on a normal distribution curve, mu is right in the middle, that's 0. Give or take 1. So plus 1, plus 1, plus 1. So my standard deviation is 1. So mu is 0. My standard deviation is 1. And then I usually just hit enter. It puts it in there. You got to hit enter one more time. And it tells you the exact Z number you're looking for. We said negative 1.96. That's pretty close. This is more exact here. So like I said, if you can't get your answer to quite work out, you might try using a more exact Z or T number in your calculations. All right, so keep all that organized information handy for the difference in the average time between eruptions. So this was group 1, this was the older time period, this is the more recent time period. They are different. Difference means, how far apart are they? They are different, but is it significantly different? So if I'm talking about a 95% confidence interval and I'm speaking in Z, if I'm speaking in Z score, I'm talking about the area between the 196s. So I'm saying the difference of the population means is between negative 1.96 and 1.96. Now that doesn't do me any good. We're speaking Z there. I need to convert it to X numbers. I want to speak with the numbers that are in the story, that are in the word problem. So what I'm looking for is I want the difference of the means to be between, and I need two numbers that relate to the story, all right? I don't want the 196s. I'm just going to need those for the calculations. I want the actual numbers like, minutes between eruption, the numbers that relate to the story. Let's start with our general formula. So the difference of the population means is between, now remember we're guessing at mu. Mu is never actually able to be calculated. So we're going to guess at it by taking a sample. These are kind of the eruptions we could measure. Mu kind of represents all the eruptions ever in the whole known universe since the beginning of time, since that thing began erupting. We'll never know what the average time between eruptions is, all right, because we can't measure all the way back to the beginning of time. But we're going to try and guess at it. We're going to take a couple of samples. We're going to find the difference between those averages on our sample. And then we're going to say, well, I think, this is our best guess, I think that mu is these two numbers, but give or take a little bit of insurance, a little bit of margin of error. All right, we're going to give ourselves a little bit of give or take because we're not certain. All right, we're 95% sure that it'll be this number, give or take a little bit of insurance. All right, so it's kind of like a point spread. All right, we think the final score of the basketball game is going to be this, give or take, 3 points or whatever, the point spread. So we give ourselves a little point spread, a little insurance, because we're not 100% sure. We're only 95% sure. Here's the more specific formula. So we got the difference between group 1's average and group 2's average is between, all right, the difference in our sample averages minus our z-score, 1.96. Don't worry about the negative. The plus and minus are taken care of in the formula. And then times, and this is an adjusted standard deviation formula. So the standard deviation for the first group, which we have to square, standard deviation of the second group, which we have to square, and then later we'll take the square root to undo that squaring, divided by the size of each group. All right, let's plug in some numbers here. So group 1's average, this is x bar 1, comes right off your list. 61.8 minus 69.8 minus 1.96 is my z number, the z number that brackets the 95%, times, all right, group 1 standard deviation that was given, 8.56, don't forget to square it. Group 2 standard deviation that was given, 11.57 squared. Group 1, that was 8,980 observations. Group 2, 23,936 observations. Over here on the right, it's the same thing except minus becomes plus. Okay, minus becomes plus. So minus a little bit of error, plus a little bit of error, or give or take, our point spread. Pop that in your calculation and we say the difference between group 1's interval and group 2's interval is somewhere between negative 8.23 and negative 7.77. Now, what does that mean? Let's interpret that. So our conclusion is we're 95% confident that the interval, let's stop there. You see confidence interval right there? That's where we get the name. We are 95% confident that the interval between these two numbers contains the actual difference, the actual population difference. We are guessing, all right? Nobody knows what the true average interval is, the difference is between these two intervals, all right, between these two measurements. But we're going to guess at it using our samples. We think that this is between these two numbers. Now, since both numbers are negative, here's where we kind of interpret our conclusion. Since both numbers are negative, we're 95% confident that group 1 is significantly lower than group 2. And then we just kind of restate that, relating it back to the problem. We're 95% confident that the interval between eruptions was shorter in the older time period than it was in the more recent time period. All right, let's try a couple more here. Do professional football players, on average, weigh more than professional basketball players? And they want a 99% confidence interval. All right. Now, just off the top of my head, I'm thinking about a professional football player and I'm thinking about a basketball player. These guys are kind of really muscular and these guys are kind of tall and skinny. So it kind of makes sense that football players weigh more than basketball players. But is it different enough to be significant is what we're trying to test. So here's a set of data for both of them. All right, just pause the video and copy this down. Here's a bunch of weights, our sample weights for football players, the pro football players that were easy to grab and weigh. We grabbed them and weighed them. Same thing with the basketball players. Your sample is just the ones that you could catch, all right? If we're measuring foxes in the wild, we can't catch every fox in the whole population, but we can catch a few of them, all right? So these are like the foxes we could catch, the football players we could catch, the basketball players we could catch. That's what a sample is. Go ahead and copy those down. All right, and then as you organize your information, let's organize it and let's see what we know and what we don't know. I know that group 1 has 21 values. I caught 21 pro football players and I was able to weigh them. My population average and my population standard deviation, those are both unknown. They didn't tell us either one. We never know mu, all right? That's what we're kind of guessing at with our sample. So we're trying to use our sample average to guess at what the population average is. Now, population standard deviation, sometimes they give that to us and sometimes they don't. In this case, they didn't give it to us. What that tells us is we're going to use a t-score, a t-value, instead of z. So we're going to use t. All right, our sample average, we have to actually calculate this. All right, I need to add all these guys up and divide by 21. So you can do it the long way, but I'll show you a shorter way here in a second. And then our sample standard deviation is what's our give or take. We're saying group 1, the football players, on average weigh about 259.9 pounds, give or take 11.9 pounds. Standard deviation is your give or take. Now let me show you how to calculate that on your calculator real quick. All right, so what I'm going to do is I'm going to press Stat, and I'm going to press Enter for Edit, option 1. That takes me to my table, and in my table I'm going to enter all of my pro football player weights. Once you get those entered, you start over at Stat, you go over to Calculate, and I want option number 1 where it says One Variable Statistics. It's going to calculate all the statistics that I need. It's asking me, are you using list 1? Yes, I'm using list 1. Don't worry about frequency list, and just get down to Calculate and make it calculate. And it pops up with all these useful numbers. X bar, that's where I got the 259.904. And then S, that's my sample standard deviation, 11.91, etc., etc. I always like to write down all of the numbers. All right, now you just do what your teacher tells you to, but I like to write down as many as I can, as many as are on my screen, because the more numbers I use, the more decimal places I use, the more accurate my answer will be. But just do what you're instructed. If they tell you to round to 4 decimal places in your calculations, then all you need is 259.9048 and 11.9118. If they tell you 4 decimal places, just do what you're told. I like to use as many as I can because the more accurate your numbers are in your calculation, the closer your answer will be. All right, and we do the same thing for our basketball players. All right, Stat, Edit, put the basketball players in the table, Stat, Calculate, One Variable Statistics, and you get these 2 numbers right here. The average of your sample, these guys, is 205.947 pounds, give or take, that's sample standard deviation, give or take 12.82997 pounds. They asked us for a 99% confidence level. Since we don't know sigma, we have to use the t-table. We're looking for a t-value. So the t number that fences in a 99% confidence interval is 2.878. I'll show you a couple of ways of looking that up. This one I got from the table, and this one I got from my calculator. All right, so I grabbed my t-table. Now, notice I have 2 different size groups. I had 21 football players, and I only had 19 basketball players. For this calculation, we're going to use the smaller group, and remember, degrees of freedom is 1 number smaller than your group number. So degrees of freedom in our table is going to be 18. All right, so I have 18 degrees of freedom on my table here. I go down to 18, and then I want to go over to, let me hold my place here, over to 99% confidence level, C for confidence level. So a 99% confidence level, and that tells me that this number right here, 2.878, is the number that will fence in 99% of the area. So from negative 2.878 to positive 2.878 will fence in an area of 99%. That's using the table. Let's go ahead and grab the calculator, and just for grins, I'll show you how to get a more exact T number. Now, the only reason I'm doing this is sometimes if you use the table T number, your answer will be off just a smidge. I mean, just enough so that you don't get the answer exactly that the book said or whatever. So if you work it all out with 2.878 and you're off just a smidge, you can't get your answer to match up to the book answer, well then go back and just make your T more accurate. So it's pretty easy to find this number on your calculator. All right, now think about your visual here. They asked us for a 99% confidence interval. So I want to know from here to here, I want it to bracket in or fence in 99% of the area. So I'm looking for this T number and this T number. Now remember, on the calculator, if I'm looking up this number over here, I'm looking up the area to the left. So I need to know how much area is in that white tail right there. Well, if there's 99% in the middle, that leaves 1% left over. And I got to split it in half because half of it goes here and half of it goes here. So half of 1% is 0.005. So what I'm going to look up is what T number produced an area of 0.005. All right, I go to my calculator. I'm going to go to distribution again. So distribution, so second distribution. And this time I'm going to do a backwards T. Remember inverse? Inverse means backwards. Usually we tell it the T number and then it tells us the area. But if we go backwards, we tell them the area and we ask them what T number produced that. So I'm doing a backwards T. I'm doing an inverse T. Choose that. I want an area of half of 1%. If it was 1%, that second number would be a 1. We want a half of 1%, so it's 0.005. How many degrees of freedom? 18, because it was our smallest group was 19. Take away 1, degrees of freedom is 18. We go ahead and paste that into our window, hit enter one more time. It thinks for a minute, and it tells me the Z number that produced an area of 0.005 is negative 2.878, blah, 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 all of those. And then its positive twin is the other fence that brackets in 99%. So like I said, usually you don't have to do that. I mean, I would probably try it with the 2.878 first. Just take that out of the table and use that. And if you have no problem making your answer match up, then life is good. Don't worry about it. But if you can't get your answer to quite match up, go back and find a more exact version of this T number. Okay, so here's our problem. We want a 99% confidence interval for the difference of the means. This is the population mean for the football players. This is the population mean or the average for the basketball players. I want to know if the difference between the two is between negative 2.878 and positive 2.878. Well, that's great, but we're speaking T. We need numbers that relate to our story, to our weights in our story. So I need to change these T numbers to X numbers. I need to change them to story problem numbers, to weights. So I need to know what the difference between the average weight of each group is between what and what. That's what we got to find out. How big a difference is there between the two groups? Start with the general form of your equation. The difference between the average weight of group 1 and the average weight of group 2 is between, well, we don't know, all right? We don't know what the average weight of any professional football player is because I can't grab all the professional football players in the world, all right? I just don't have the time. We can't get that measurement, but we're going to guess at it. This is our best guess. I'm going to guess at it by grabbing a few football players. We grabbed 21 for our sample. And I don't know the average weight of every professional basketball player in the world. I can't gather them all up and weigh them. That's impossible to do. But I'm going to guess at it by grabbing a few basketball players, those 19 that I grabbed. So we're going to make a guess at the difference between the true average weight of football players and the true average weight of basketball players. Whatever that difference is, we're going to make a guess at it by taking a sample and subtracting them. So the difference between our samples should be pretty close to the difference between the true average weight of football players and the true average weight of basketball players. So it's our best guess minus a little bit of error plus a little bit of error. So we think that this is our best guess plus or minus a little give or take, a little insurance, a little point spread. We call it margin of error. Here's your, here's your precise formula. So the difference between the two population averages is between this mess over here and this mess over here. So our standard error is our T number times an adjusted sample standard deviation. All right, pop the numbers in here and then we'll draw some conclusions. These come right off your information. All right, just pull it right off that organized information. The only difference over here is, whoops, that's supposed to be plus. Let's change that. Yeah, I'm having trouble. I probably should have paused the video. That's a plus. There we go. All right, that's better. So minus a margin of error, minus a margin of error, plus a margin of error, plus a margin of error, plus a margin of error. Grab your calculator and calculate it, 42.66 and 65.26. So the difference between whatever the true average weight of any football player, professional football player and professional basketball player, whatever the difference is between those true averages that we'll never know, we think it's between 42.66 and 65.26. Let's draw a conclusion now. We are 99% confident that the interval, there's confidence interval, we're 99% confident the interval between these two numbers contains the true difference, mu1 minus mu2. Whatever the true average weight is minus the true average weight of the other group, whatever that difference is that we'll never know, well, we made a pretty good guess, and we're 99% sure that this is between these two numbers. All right. That's kind of our point spread. We're making a bet. We're 99% sure we'll win this bet. We're 99% sure that this difference that we'll never be able to calculate is somewhere between these two numbers. We're really, really sure. Since both numbers are positive, we are 99% sure, 99% confident that group 1 is significantly heavier than group 2. That's kind of what we thought. We just wondered if it was significant. And now just relate it back to the word problems. We are 99% confident that professional football players have a significantly higher average weight than professional basketball players. All right, and I just threw another one on here for you guys to practice. You can pause the video and work it out and practice if you like. Does one region have more phosphorus than another region? All right, they took random phosphorus samples from two regions, and they want an 80% confidence interval for the difference between the average phosphorus level of region 1 and the average phosphorus level of region 2. And here's your phosphorus levels. So region 1, region 2. Remember, sigma's not given, so you're going to have to pop these in your calculator and get S, your sample standard deviation. So I'd go ahead and pause the video, give that a shot. And then I'll go ahead and run this through kind of fast because we've already been through it twice now. So here's region 1, here's region 2, here's our numbers. We don't know anything about the population. We don't know the average, and we don't know the give or take. We don't know the standard deviation. If you don't know sigma, then you use the T table. These came off our calculator. Pop those numbers into your table and have it calculate one variable statistics. Same thing over here. Use as many decimal places as your teacher tells you to, all right? But remember, more is better. The more you use, the closer your answer will be. And then finally, T off the table is 1.363. If you want to bracket in 80% of the curve, if you want to fence in 80% of the area in the middle, that's negative 1.363 to the left and 1.363 to the right. Here's a more exact version. Again, I wouldn't use this. I found this on the calculator. I wouldn't use this unless your answer is off just a smidge and you can't figure out why. Maybe you used all these numbers and you used all these numbers and you still can't quite get your answer to match up to what it's supposed to be. Well, then go back and change your T to a little more exact version of T, and that should fix it and make your answer match up. And here's the rest of that problem. So 80% of the curve is between these 1.363 numbers. So the difference between the two regions, difference between the average of region 1 and the average of region 2 lies somewhere between these two numbers if we're speaking T. We don't want to speak T, we want to speak X. I need numbers from the story problem. So I'm trying to convert these two numbers to numbers that are in the story problem. Using my formula, all right, and we plugged all the numbers in here. Let me make it a little smaller so you can see it. There's all my numbers, all right, 747.5, 738.9375 minus, there's my T number, 1.363. Remember, don't worry about negative or positive. It's taken care of in the formula. There's minus, there's plus. S1 squared, S2 squared, 12 in the first group, 16 in the second group. Same thing over here, except it's plus. Plus a little bit of point spread, minus a little bit of point spread. So we're trying to guess at this using our sample. Our sample is our best guess at mu, and we just give or take a little bit of insurance, a little bit of error. All right, so we think that the difference between the averages is somewhere between negative 90 and positive 1.0 or 107. We're 80% confident that this interval lies between these two numbers. Since the intervals have both positive and negative, we can't make any decision. It's too close to call. Right? If one is negative and one's positive, that means I can't say the first group is significantly lower, and I can't say the first group is significantly higher. I can't say either one because we have a mixture of positive and negative numbers. So I just have to call it a draw. There appears to be no significant difference in the phosphorus concentration in these two regions. There's my final interpretation of my results. All right, one appears to be lower, but it's not significantly lower. So we're just going to say there's no big deal.